It's recording? Okay. All right. Well, welcome back, everyone, to the new term seminars. We had to change the time due to some time conflicts and availability of the co-organizers. So it'll mostly be on Monday. I think it's always going to be on Monday now for this term. And if you have any time conflicts, let me know so I can see what we can do. But yeah, may the 4th be with you. And so this is a continuation of what we did last time, which was learn some TQFTs. And it's I'm going to follow the same source I was doing last time by Lucas's course, which is... I can't? Oh, really?
Oh, there, you just got it to move.
Oh, yeah. I think it was just capturing it. It's, right. Same resource, and right, last time we gave a bit of a motivation, then we started talking about categories because that was the natural language that we needed to talk about TQFTs. We defined what a TQFT is, symmetric monoidal functor from the category of cobordisms to vect, and then we said, okay, now we got to learn what a category is. So we did that, and I gave some examples. We talked about functors, which is good, and we got up halfway through the notes that I uploaded on the website, and we got up to natural transformations, but I'm going to give a very quick recap of what a functor is. So I'm not even going to go through the definition, just going to draw the picture. So we have category C, and the CIs for all i's are objects in our category C. And we have homs between these objects in our category, F and G. And what the functor does, it maps from an object from category C to an object in category D, or denoted as D1, and D1 is the functor applied to the object in the category C, and also D2, same thing here. I'm not gonna write it down, and D3 here, which is same thing there. You can fill in the details. We talked about it last time. Just a quick recap. This is my functor. It also sends homs in this category to homs in this category. So this is going to be the functor applied to F and the functor applied to G.
This is a particular case, not right? This covariant case.
Exactly. The covariant case we talked about. The contravariant case is just that this the codomain of the functor on the homomorphism is it reverses the direction. So this arrow will be pointing upwards. Same with this one if it's contravariant. But when I say functor here, I just mean covariant functor, and that's the one we'll stick with. What else? It has the composition rule that this is GOF. Sorry for going between the line, the border here, and also we have going from here to here is GOF. So yeah, the functor applied here. This is the compatibility rule for the compositions. This is what it does. Should fill in the this here. So, yeah, the functor goes between the two categories as the objects and the morphisms. And this is what it does pictorially. So we did this last time, and now define what a natural transformation is. Where do I have my natural transformation? Right, okay. So here, okay. Definition 1.11. So F and G are functors from my category C to my category D. And what else? So a natural transformation, which we'll usually denote with eta, goes between my two functors, right? And also has, if I apply it to an element in the category C, this is how I denote it. It means that I'm applying it to, well, okay. It is a map between the functor applied to the object C in the category C. So this thing is an object in the category D. And it's a map from that to the functor G applied to, see, I gotta really try to stay in the lines. But yeah. So for all objects C, the category C. Okay. And yeah, so this, again, this is an object in D, and this is an object in D as well, such that we the following diagram commutes. C, apply the eta at C. To GC, go down. And so this is a hom in the category C, so applying the functor takes me to homs in the category D, right? Same thing applied here. And I haven't defined what C prime is, though. It's just a category in, so it's an object in the category C. Whenever I have C sub something or C prime, just take it to be objects in the mathcal version of that letter. And this C prime goes to this. And so C and C prime in are objects in the category C, and also for all Fs which are homs from C to C prime, objects in the category C. Yeah. Good. I can also just write it as this. A more mathy way of doing it. Let's just do that. C to C prime. Okay, very good. Now, okay, so this is a natural transformation. End of definition. And right, so the whole idea of category theory, as we said, is that a category is made out of objects, and So made out of things which we call objects and relations between them, which are our maps, our homomorphisms, and this goes between the map between the categories. And you can do this, take this level of abstraction higher and higher, and keep doing this game forever sometimes. But for now, we'll just stick to natural transformations. And if a natural transformation is an isomorphism, it's we call it a natural isomorphism. That's also another definition that I won't bother to write down. Just if it's an isomorphism, we call it a natural isomorphism. And so, okay, we.
Does that just mean it has an inverse?
Yeah. Isomorphism bijection, so would have an inverse, yeah. Exactly. Nice. Very good. Okay. I think we did this last time, if I remember correctly. Sorry, it's been a while. Or just briefly mentioned it. But okay, any questions so far? Okay. This should be new territory now, I believe. So, let C and D. I still don't know how to write a math calc at D, but be categories. Categories. And so there's a category of functors. A category of functors which is denoted as this between category C and D. And so the objects here are functors between these categories. So let's write it out. Functors between C and D. This whole thing is an object in this category. This category. And the morphisms are natural transformations. So F, then using eta, you go to G. And using eta prime, let's say, call it, go to H. So yeah. The functors are objects, and the map between them is are natural transformations, and such that this diagram commutes. It's going to become a little bit messy. Natural transformation. G, and then H. So yeah, this thing commutes, so you can go like this, or you can go like this, or like that, and there's a natural transformation given between these functors, between these categories, and yeah, this is the yeah, this is the category of functors. Okay. We also talked about the double dual last time, but I guess I don't think I wrote it down, or maybe that was the last thing I did. The double dual being a map from vect to vect, and it's denoted like this. One star is a dual, so this is the double dual, and it takes. Okay, so write it down. So what does the double dual do? Well, it takes in an element of the dual to the field of the vector space. And what is the dual? What does the dual do? It takes in. It's a map from the vector space to the field. So the double dual takes this whole thing, this f, to the field. And how does it do that in a natural way? We just apply f to v, and this gives the natural isomorphism. And so there's an identity map functor from the category to itself. And so what we're saying is that there's a natural isomorphism between the identity and the double dual. And this is very nice. This is very nice. It exists for finite dimensional vector spaces. For finite dimensional vector spaces, they are isomorphic to their duals, but the isomorphism is, there's no natural isomorphism unless you have a metric. For the case of Hilbert spaces, you have an inner product induced metric, so you use that to find a natural isomorphism between vector spaces and their duals. But for here, you don't need that. Okay. Okay. Definition 1.4. Sorry, 14. A functor. If my handwriting is illegible, illegible, is that correct? Illegible? Illegible. Please let me know. Right. So, this functor is an equivalence if and only if there exists f inverse from D to C and also a natural transformation. I'll denote that with natural transformation such that f is, there's a natural isomorphism to the identity on the category C also, and if we do the other composition, it should give us the identity on the other side. So, up to natural transformation. Identity on D, yes. So, right, you have a functor between this category to this one, and its equivalence if this thing exists going the opposite direction, and also the natural transformation that's here, such that if I do f first, then f inverse, there's a natural isomorphism between that composition of maps and the identity on C, and likewise the same thing, just you go first here, then here, there's a natural isomorphism with the identity functor on D. Okay. Later on, we'll see when we talk about symmetries how a group acts on a TQFT and that's given by the category of groups, a map between the category of groups and our TQFT, which we said is a functor from cobordisms to vector spaces. So I'll just write that out. So recall that this was the category of groups. If don't remember, it's fine. We're not going to use it for this talk. So it's just stuff we'll see later, which I'll give a quick recap when we do get to it. And this is Buddhism and category of vector spaces. And so a TQFT is an object in here, in that category, the category of functors from the category of cobordisms to the category of vector spaces.
So is that the category of all groups or for a given group?
What was the other option?
BG, like you would pick up a single group, like a chosen group, or is that like a group realized as a group wide?
A group realized as a group.
Is BG the category of all groups?
Category of all groups.
What is it?
How do I define BG again?
Usually the category of groups has different notation. So
Yeah.
As different notation?
it's usually just GRP.
Yeah.
This looks like the classifying space.
It does. It does. But in the lectures, he said they just call it the category of groups. But okay. So for this,
I think in your last lecture you said that this had a single object.
yes,
That's what I'm imagining. It's like
Yes.
a group where it's like one object and then the morphisms are the elements of the group.
Exactly. Yes.
That's what this is. So G is a group, and you turn this into like a single object category. And
Yes.
a functor into, okay.
yes, yes. So might as well write it out. So BG, the objects of BG, BG are just a single element. We'll denote it with asterisk, and the morphisms of this are the group elements. And so we want this following diagram to commute. This is H and G and H and G. And H and G are both elements of our group. If commutes if and only if. Okay, so. But wait a second.
It should just be that the group operation is, like the composition operation is the group operation.
Yeah, the composition should be the group operation, right? Ah. Right. This is right. This was an example, not the definition. Right. So that part is true. The morphisms are G, and how you go between objects of that is by using elements of the group, and the composition HG. So the composition is defined, as you said, with just group multiplication. Right. So the composition rule is given with that, and the identity is the identity of the group. Yeah. The identity on the objects is the identity of the group.
You made a comment earlier. So
Right. TQFT is an object in this category. Yep. Yeah. Honestly, I shouldn't really have mentioned this because we're not really going to use it here. We're going to use this later, so this is kind of my bad. Sorry. But yeah, yeah. We did a bunch of examples using BG last time, but it was a while ago and I didn't refresh my memory about that. So, okay. Where were we? Right. So now we want to get to the monoidal category part. It's nice because now we're starting to see the words that we had for the definition of a TQFT. Okay, so let's define this first. So C and D are categories, and we define the product of these two categories by with their objects and morphisms. The objects are, I'll just write it like this: objects are C and D. Yeah, D. And C is an object in C, and D is an object in D. Write that down. And C, object in D, and the morphism in G is given by the morphism of in each of each category, like this. Okay. And so the right F is home in C, G is home in D, and F and F with G. How do they act on elements? Well, they take C and D and take them to C prime and D prime in again categories C and D. And the composition is of this with, let's say, H and let's say F prime and G prime is the same thing here. You just do it on the first entry and on the second entry without mixing them. Okay. So now we can finally define what a monoidal category is. A monoidal, spell that correct, yeah. Category consists of category C and unit object, which is an object in the category C, and a functor that takes in 2 copies of C and spits out an object in C. That's why we define the product of categories. And a natural transformation and right to do right transformations, natural transformations are in L such that we have the, well, okay, just write down the diagrams. So this is telling me that the first one is just the unit, and the second one I take in whatever this input is, and so this gives me C cross C. And then I apply the functor, the monoidal product, and I get C back, right? Because that's what we said it does. And so as we know, there's a identity on C, and all we want is that this to be to exist a natural isomorphism that we denote with R to the identity, and it's R. We call it R because R on the category. Well, R applied to an object in the category C takes in 1 tensor C, and there's an isomorphism between this and C. So yeah, R I think is short for right unit, if I remember correctly. Right. Uniter, right. So that's why we say R, and the same picture exists for L, just from the left. So it's going to be C this time, just swapping this from the left, taking whatever is here on the right. I put the unit. Again, it's going to give me C cross C, and this using the monoidal product takes me to C, and so there's an identity again, as always. Hope the camera can catch that. If it can't, let me know. And there's a natural isomorphism that we call L. So L is like this, but just swap that. Can the camera see that?
Yeah.
Okay, good. So, yeah, the definition isn't yet over, so there's and we have this really nice comedian diagram. So I want the first two to, for my monoidal product to take the first 2 copies to 1 copy of C, and I want on the other one, this one, the third one, just to do identity on it. So I get this. Similar thing here, just in the other order is I want identity on the first one, and on these 2 I want to use the monoidal product, which is going to be C times C. C looks like an E, sorry. And the monoidal product takes in this and gives me 1 copy of C. That's better. Same thing here. And so I want there to be a natural isomorphism alpha from here to here. From this to that. Natural alpha. And the only thing is in the notes, there's a typo. I forgot to put alpha there. I'll go re-upload them at some point, but there should be an alpha there. Without that, because we use alpha right after, and so if I don't have alpha, you might wonder what is alpha. But yeah, that's the natural isomorphism there. So, okay, nice. Now, okay. Right. We're not done. We're not done. We have these things, but we need some compatibility conditions. So the such that is still left. Such that we have two commuting diagrams, which essentially tell us that the bracketing doesn't matter, which is a nice condition to have. That means you don't have to worry about bracketing. And so, yeah. And to say that rigorously, we need these commuting diagrams. So the first one is if I have x and 1, and I bracket it like this. So I start off with this type of bracketing, right? Now, I apply alpha sub x, 1, and y. These are the three elements. It tells me the other way that I can bracket this, which is what? Instead of bracketing the first two together, I bracket the second two together. So it just moves the bracket from here to here. That's it. Okay, nice. Now, also, if I act on this with the right uniter on this and identity on y, so I do nothing to y, what do I get? Well, the right uniter we said here just sends this to x, and well, y I said I'm doing nothing to just identity, so I get y back. Now I do a similar thing here, except with the left uniter. So it's going to be identity on x tensor with left uniter y. And say, oh, sorry. One cross y goes to y. So that's the first commuting diagram. And the second one is what's usually known as the pentagon diagram. It looks pretty complicated because it's pretty big, but it's not very complicated. Once we go through it, you'll see that it's very intuitive. And I didn't dry out my the cloth on this eraser before coming here. I didn't dry it out properly, so it's kind of smudging. But I hope it's not too annoying, the smudges. Okay. So, right, the pentagon diagram. So we start off with, hope there's enough space. We start off with this type of bracketing of this expression. So we have y cross, w cross x, and it's going to be y and z. So we got 4 elements. And so, how do I make this fit? I'm going to go up like that. So I'm going to apply alpha of, I'm going to treat this as one object. And so it's going to be alpha of w cross x. This is one object, so you can, if it makes it easy for you, just like kind of cross it out, just to see it as one object. And y is the second object, and z is the third object. So because this is one thing, how it's bracketed, you look at these brackets here. The first two are bracketed, so what alpha does, this natural transformation, it takes this and puts it here, the brackets. So instead of the first two objects being bracketed, it makes it the second two. So it becomes this. W cross X and tensor Y Z. Okay. Right. So far, so good. Okay. And then apply alpha again. This time we treat W and X as an object and Y cross Z as one object. So this is one object, and so we got to look at these brackets. It's bracketing the first two objects. So now I need to move this bracket to the second two. So it's going to bracket X and this object, Y cross X. So it's going to be W cross X, Y cross X. Sorry, Z. I meant to say Z. I think I said X. Honestly. Right. All I did, this is one object. The bracket is on the first two. You just move it to the second two. So X and this one. Now we're going to do kind of the same thing. Well, similar to it. Now I'm going to move the brackets in here. How am I going to do that? Well, I'm going to apply alpha to W, X, and Y. To Z, I'm not going to do anything. So identity on Z. What is it going to do? So first two, so I'm going to look in here. The first two are bracketed, move it here. The second two are going to be in the bracket. So, right, this, we don't do anything to it. So this is going to be W cross X cross Y. Because I move the bracket here to here. And this, I do nothing to it, stays a Z. Okay. Good. Now what am I going to do? Okay, apply alpha to W, X tensor Y, and Z. So this, again, is one object. So just imagine this is one object. And so I'm going to look at this bracket. The first two are being bracketed. So I'm just going to move this to the second two. So it's going to start here and end here. So this is going to be W cross Y cross Z. Nice. Now, bless you. Now, okay. To go to here, what do? I apply, well, I do nothing to W because I want it to stay like that. So identity on W. And on these, I just do my natural transformation alpha. Y and Z. So what this does is that the first two are bracketed, it moves it to these second two, I get that. And these two commute. So what this is telling you is that it doesn't matter how you bracket things. Just it is the rigorous way of saying that. So it's pretty nice. End of definition. This was our lengthiest definition yet, but it's very nice. Any questions so far? Good.
Basically, what you're saying here is that you can give categories. It looks like the product structure found in like an algebraic monoid, right?
The product structure is what?
Like if you look at like a monoid in just algebra, you're just saying that
Right.
you can define an analogous product structure
Yes.
on categories.
Very good.
Yeah.
Exactly. Yes. Yes. That's how I think the naming came about.
Yeah.
Probably. But
In a very precise sense, this is the one level up definition of a monoid. Right? It's exactly what it is.
yeah, it's very nice. just for fun fact, a monad is a monoid in the category of endofunctors. I just like saying that. There's other ways you can define it that are more meaningful, and I think G++, is that his name, or sheafification? I forget. He has a video on that, on a monad. So I think if you just search up monad on YouTube, you'll see that video. It's a very good video. Maybe I should give a talk on monads at some point. But yeah. Okay, so this is a monoidal category. Very good. So the monoidal product in the category of sets is the Cartesian product, the set product that you've seen. For categories, it's the one that we did here, and for vectors, it's the tensor product that you're used to. Okay. Just as like a remark. And how are we doing with time? Oh, it's been nearly an hour. Okay.
Why do they call it monoid if you take two objects to one? Like, that's what I would call a binary operation.
Binary operation. Well,
That's the binary operation of the monoid. So the monoidal category, the data of it is the binary operation together with the unit satisfying some conditions, right? Like a monoid normally is a set of objects, a set of things, a binary operation, and a unit such that it's associated with unit, right?
If you say so.
Yeah, like
yeah.
that's the definition of a monoid.
Yeah.
And then this is the definition here. Did you have something else?
Well, is there something you would call like a bioid or trioid?
Oh.
Versus monoid.
Oh, that's a
I'm not
good
sure
question.
where that name comes from, actually. But like,
Oh, you do have a good point. Yeah, I never thought of it like.
I mean, the whole point of a monoid, though, is like it doesn't matter what you can multiply n elements together, and it doesn't matter how you bracket it, right? So like with a monoid, you put n area operation too, right? But associativity means
Oh, yeah.
like it doesn't matter where you apply things in, right? So yeah, that's like another thing about it. So
Hmm.
All are one.
yes, all are monoid.
Yeah. Oh yeah. Yeah. Nice. Nice. Yeah. Good question. Thank you. Very nice. Okay, so now we could talk about braided monoidal categories. It's gonna get even more fun. Okay. Yeah, these things really take longer than I think. Like, the first one wrote 16 pages. I was like, still gonna like not have extra time. I haven't prepared enough material, but I only got up to the first 8 pages, and now an hour has passed, and almost an hour is like page 11. Crazy. Anyways, definition. Definition. Point 18. So, a braided monoidal category consists of a monoidal category that we just defined, call it C, a natural isomorphism, natural isomorphism, B, or beta, or I think it's mathcal B technically, or do Greek letters have mathcals? Mathcal beta, is that a thing? Yeah. That's fair, yeah. So, Yeah, I think it's mathgo B. And right. So another acute diagram. So we have C cross C. Then the monoidal product takes us to C, one copy of C, and there's a sigma here. And what sigma does, I'm just gonna write it right under it because like object-wise how it acts on things. It takes C cross C prime, different objects in C, and it just swaps them. So it's it just swaps them. That's it. Nothing too fancy, right? And so this goes to, well, again, these are still objects in C, so I'm still gonna have C cross C. And again, the monoidal product takes me to one copy of C. And beta is the natural transformation here, or B, or yeah, which we call the a braid, or braiding, called braiding. So yeah, B is the natural isomorphism that does this braiding. And sigma flips, and so now we have a bunch of commuting diagrams that again might seem a lot at the beginning, but once we go through each step, we'll realize that it's nothing too crazy. So, called braiding, and we have these following commuting diagrams. So we start off with a specific type, a specific bracketing of these objects. And okay, so I apply alpha. I can put the indices, but there's no need because the only thing that can go as the index of alpha is x comma y comma z, right? So it's kind of don't need it because it's implied. So it moves this bracket to here, to the second two. So I get what? X tensor y tensor z. Or I guess it might be better if I say O times. I don't know. You guys know what I mean. It's the monoidal product. Now, I applied B to it. But to which elements? Okay. B to X, and I'm treating y tensor z as one object. Right. So this is one object. The braiding is going to swap these. So I'm going to get y. Why is my handwriting getting so much worse? Y tensor z, tensor x. The B just swaps them. Very nice. And now I apply alpha again. It's implied what's the indices of alpha? It's y comma z comma x. The only thing that can go there. So it's going to it moves this pair of brackets to here. So it's going to be y tensor z tensor x. Now I'm going to do similar thing here, but now I'm going to swap these using the braiding. So I'm going to apply the braiding to x and y, x comma y, and I'm just going to leave z alone. So identity on z. Okay. So y and x are going to get swapped. It's going to be y tensor x tensor z. Now, I apply alpha here. Again, alpha, there's only one thing that can go for the indices, y comma x comma z. So this is going to become, moves the bracket from here to here. It's going to become y tensor x tensor z. And to go from here to here, what do? I leave y alone, but this I have to swap it. I use the braiding. So it's identity on y and braiding on these two. Braiding on x, comma z. Very nice. We get this. I'm gonna give this a name, star or asterisk. Give that the name for this condition. And the second condition is something very similar to this, but to be rigorous, let's write it out. X tensor, y tensor z. Now, I use alpha inverse here. What does alpha inverse do? The opposite thing of here. Alpha takes in the pair of brackets on the first two objects to the second two. Alpha inverse does the opposite. Takes in the pair of brackets acting on the second two to the first two. So it's going to move to here. It's going to be bracket x tensor y tensor z. And now going to act on this with the braiding. So how am I going to braid this? Well, I'm going to braid this as, I'm going to treat this as one object. So it's going to be x tensor y, and z. So one object, and the z is going to come here, and it's going to become z tensor x comma y, x tensor y. Okay, now I use alpha inverse again, move this bracket here, and by now hopefully you know that all the indices for these alphas are very obvious, z comma x comma y. So this becomes what? The bracketing changes to the first two being z tensor x tensor y. And now, for here, I'm going to leave x alone. So it's going to be identity on x and tensor the braiding on these two, y comma z. So what's this going to become? Well, the first one I leave alone, x, and these ones get swapped, so it becomes z tensor y. Okay, now alpha inverse again, right? It's going to move this here. It's going to become x tensor z tensor y. Now, how do I go from here to here? I'll leave y alone, so identity on this one. But these I gotta swap, and I'll use the braiding. So it's going to be braiding on x and y, x and z, and tensor identity on y. Nice. Now I'm calling this double asterisk. Just calling this condition that. And commute for all x, y, z in objects of our monoidal category. Awesome. So we talked about what a monoidal category is, and the braiding just swaps things, and now we're gonna write stuff down very pictorially, and hopefully that'll help the intuition more. Yeah, yeah, that's the exact next thing that you mentioned. We call that symmetric, right? So, right, it's gonna. That's exactly the next thing we're gonna define. So.
Yeah, so for people who might be thinking of monoids here, we're coming towards
Yeah. We're gonna define the symmetric braided monoidal category to be what you said.
Just in general, like braid and unbraid, and like a general braided monoidal category that's not.
Oh, the general no.
You can apply the braiding and then it's inverse, and of course it's
It's
inverse.
inverse.
But if you apply it twice, it's not the identity, not necessarily.
okay.
So
Yeah.
like I
So
don't know.
it's kind of like when you think of a braid, like braid something more than rebraid, and it's not.
Yeah, so you could like have multiple.
Yeah.
Right. So I don't know if you're going to talk about the Yang-Baxter
Yeah.
equation. Yeah.
Yeah.
So I'll let you.
Yeah, yeah. These are all things that come together. But yeah, the reason why you braid twice, you don't get identity is this, which we'll get to. But since you just asked, thought I'd draw it. It's exactly if you've seen any kind of knot theory at all and seen the under and over crossings, it should be very reminiscent of that. And we'll get to draw a lot of these later on. And it turns out that these pictorial diagrams that we do in knot theory is a very natural way of describing all of this in an easier way that's both pictorial and less writing than all of this. The community diagrams are really nice, especially when you do category theory, but it's going to get even easier to draw. So I find it very satisfying. And we're going to do a very cute proof that if you see it, it's like, how's that a proof? But it's actually quite rigorous. But yeah, okay, nice. Great questions. Okay. Okay, so definition. Definition. Oh, I didn't number this definition. I don't know why, sorry. A braided. You know what? I'm gonna abbreviate it to a braided monoidal category. Is symmetric if and only if. So if I do a braiding on elements y, x, and okay. First do an braiding on xy, then do braiding on yx. So the composition is written like this. This is going to be a map from x tensor y to itself, right? This swaps these, and that swaps them again, and so you get this. If this is equal to the identity on x tensor y, we call it symmetric. So in the general case, it's not the identity, but if it is, we call it symmetric. And so, nice, because we in the first one we said TQFT is a symmetric monoidal functor between these categories, and so now we learned what a symmetric monoidal category is. Well, not the category itself, but yeah, we did. Good. Okay. All right. So some graphical calculus now. I'm not going to write it on this board because we have lots of boards, so might as well go here. That was too far to that side. Okay. So graphical calculus for braided monoidal categories. Braided monoidal categories. Okay. So if I have a HOM XY, right, a map between x and y, I want to denote it pictorially as this. Right, I have x, and then f takes it to y. So I'm just going to define that to be this. Right, nothing wrong here. I'm going to define, I'm going to say, if I just have x, that's like having x, then act on it with identity to get x, right? So identity doesn't really do anything. So we might as well say they're the same thing. Identity on x, you get x back. So if there's an identity, we just don't bother to write it. Now, what about f tensor g? Well, I'm going to denote it pictorially as I have x, I have y, right? Separately. And on x, I act on it with f. I get x prime back, right? X and x prime are objects in category x, and f is a hom in that category. And likewise for g, same thing goes on here, and goes to y prime. Okay, so whenever I have this, I just mean that. And for the monoidal unit 1, it's gonna look kind of goofy, but 1 is just nothing. If I have a monoidal unit, we just don't put it. We don't bother to write it now. Okay. So we're going through the rules of how to write down these using pictures. To me, it kind of reminds me of Feynman diagrams. How you do, like in the first course in QFT, you see the integrals, and then you're like, okay, this for all these vertices and edges and all these stuff. That's just this is what it means in terms of the integrals. So
Where it comes from, actually.
it does.
Yeah, I think that these diagrams come from Feynman diagrams originally.
These ones specifically.
Like the strict diagrams for monoidal categories, I think that's the inspiration.
Right.
Like mixer networks and stuff.
Right. Yeah. That makes sense. I think, if I remember correctly, okay, take this with a pinch of salt because my memory is horrible. But Witten has a like hour and a half long documentary on physics. I think it's called The Story of Physics or something like that on both YouTube and Spotify. And he was talking about how with Feynman diagrams, these vertices are very problematic, and it's kind of alluding to topologically when you look at a Feynman diagram, it's not a manifold because at the vertex, right, you have this, which is the definition of a topological manifold, you want it to locally look like Rn, homeomorphic to Rn, but at the vertex, it's not, right? It's not even a manifold with corners. It's just not a manifold. And then the string diagrams resolve that. You don't have that problem anymore. You get the pair of pants. And so you don't have to worry about that anymore. Yeah. So that was really interesting to me. But it was a very nice video, so definitely recommend. I think it was called The Story of Physics by Witten.
I found it.
Okay, nice, yeah.
Diagrams also show up in like control systems engineering as block diagrams.
Oh, nice.
Yeah, there's a better you can formalize it all in terms of monoidal categories.
Awesome. That's great. Nice. But yeah, for the Story of Physics, I listened to both the Spotify and YouTube version for some reason, and one of them, if I remember, it was more complete than the other one for some reason. I don't remember. It was a long time ago. So just look at the times of both the Spotify and the YouTube one, see which one's longer. That's probably the more complete one. an example. I have this, and we want to see what am I saying now that I gave us the rules for what these things mean. We want to see what this means, the thing that I'm drawing right now. So have y, have z, have z here, and there's a g here. Let's call this u, and it goes here. Should have left more room. H, and then goes to W. Okay. So what does this mean using the rules we set here? So I'm just gonna put equals, colon equals. So I have X, then F maps it to this, right? So X gets mapped to using F gets mapped to Y tensor Z, right? Reading from left to right, Y tensor Z. Okay, that makes sense. Now, on Y, what happens to Y? G acts on it and gives me out U. So okay, so on Y, I act on it with G, but on Z, I do nothing, right? And doing nothing is the same as identity. We said here, we don't write down the identity, so you can just imagine I insert identity there because I can. So identity on Z, and this gives me the output of G is what? U, and that one's going to be Z because I did nothing to it. And H takes in this and gives me W. H gives me W. So this is what that means. Cool. Right, and so, okay. An important remark is, should write this down probably. Remark. We don't write alpha inverse L or R anymore because they're implicitly implied. So here's an example. Start with X and Z and goes up like that, goes up like that. So put a G here and W there. And there's an F here that spits out two things. One is a U that just nothing happens to it anymore, and a Y. Okay, what's this then? So using the rules, I start with X tensor Z, right? I have these two things. Now, F takes in my X and spits out what? U tensor Y. Okay, so F takes in that. What happens to Z? Nothing. So identity, right? Identity on Z. This is Z. So this gives me what? U tensor Y. And well, Z, nothing happens to it. So I end up with this. Now, what does G do? What does G take in? It takes in Y tensor Z, right? But I don't have Y tensor Z. This is like one object, this is the other one. What do? I need to use alpha. Alpha, we use it to show us that bracketing doesn't matter. So what alpha does here is goes. How do I fit this? Sorry, I'm going to do this. It looks kind of bad, but bear with me. It's going to go U tensor Y tensor Z. Now, why did I do this? Because now G can take in this thing. And U, nothing happens to it, so identity. But we're going to drop the alphas because in this picture, what's the alpha telling me is that, well, I have these two bracketed like this that came out of F, but bracketing doesn't matter. I can bracket these two together, right? So that's why we're gonna just drop the alpha inverse L and R. They're just implied. We can figure it out from the picture. Uh, and it's only useful for if you wanna not do the pictorial method and write it down using these commuting diagrams. Then you kind of need to use these ones, but you can figure it out. Okay, so here again, U, nothing happens to it, so identity on U, and tensor this, well, G takes in that, Y tensor Z, and what do we end up with? We end up with U tensor W. Okay, so. Now, there's a theorem called Maclane's coherence theorem that assures us that this will always work fine, and we can but then we can ignore these stuff that are implied implicitly for all well-formed diagrams built from associativity, unit isomorphisms. They commute. But yeah, that's. I think I looked it up at some point, but I didn't write down the details because I didn't think it's necessary. It's just something that assures us to not worry, and this will work.
It's worth thinking about like the big pentagon diagram you drew before is
Mhm.
absolutely necessary for
Yes.
these interpretations to make sense. If you draw four like lines next to one another, if that's not true, that whole pentagon, that big loop could be a symmetry that's not trivial, you know. And then like four things set next to each other could actually be like a non-trivial one or something.
Yeah, and we'll draw the pentagon diagram right now. I'm just trying to remember which one I denoted as asterisk and double asterisk. Sorry. So that's right. Not the pentagon one. It's a different one. Okay. Okay. So it's something that. Oh no, it's here. Okay. 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 So. Right. Now. This is the remark. Should probably put the thingies so people know when it ends and begins. So, new part. We have this. We have x and y. X and y. And I do a braiding. X and y. And so, what do I end up with? Y and x. Right? Y and x. Okay. So, how do I denote this pictorially? Exactly like what we mentioned before, using this. So this is defined as that. I do a braid, which is very nice because this is how you imagine a braid in real life. And so, what else do we have? Let's say we start with x and y and z, and I do this to them. So, this is equal to having x and y tensor z, and this is if and only if the that condition over there holds. And we can leave that as an exercise. And okay, so Why is that true? Let me see if I can come up with a sketch proof on the spot. So, first one, you have x tensor y tensor z, right? Bracketing, again, doesn't matter. We start off with bracketing like this in that expression, but alpha tells me I can move it to here. Bracketing doesn't matter, very good. And then I do the braid. Which ones do I braid? I braid the y and z with the x. So I take this and bring it as an undercrossing to the other side, and I end up with the top right corner over there. Okay, good. And again, brackets don't matter, so you can re-bracket it however to make that work out. Now, the other direction, let's go the other direction. I braid the first two, right? It says braiding x and y. I braid this. Okay, good, nice. I braid this, and I do nothing to z, right? On this level, it's kind of, if I put more space here, it will be easier to see. But imagine I do this braiding first, and I haven't done anything to z yet. If I just move this a little bit up, it's easier to see, but you can convince yourself on this level, I've braided x and y, and z haven't done anything to it. So I get this, again, rebracketing doesn't matter. But then I leave y alone, this is y, identity on y, leave it alone, and braid these two. I braid those two, and what do I end up with? I end up with the braiding on x and y tensor z. So it's going to be y tensor z, and then x. And then you rebracket, you end up with the bottom right corner that's there. You get y tensor z tensor x. And you end up with that. Okay. 1 second. That path is correct. Did I do it correct the other way? Now. Okay. So for the first path of that commuting diagram, the alpha tells me, okay, I can imagine these as one here. Then I do the braiding. And I end up with y tensor z as one object, and then x, but I can re-bracket it. So the first path, when I went through it, I think I did it incorrectly, but this is the correct explanation. Right. So first path, you look at this. This you can converse yourself that is the first path. By first path, I mean go right then down, and for in the commuting diagram, and the second path, the down then right, is this one. I hope that made sense. Sorry if I explained it poorly. I tried to come up with it on the spot. But yeah. Okay. Nice. So that's the proof sketch of why these are equivalent. Now, the other condition. Okay. So, the other condition, again, I'll start with x, y, and z. So, x, y, and z, and take this to be like that, take that to be like that, and take this to be like this. And this is the same as if I have x tensor y, take it like that, and z is like this. This is if and only if and only if double star or asterisk or whatever. Okay. Let's give a proof sketch for this. Okay, how does this work? Here. I have X, so I have this thing here. Let's go this path first. First path is this. Alpha inverse just tells me, okay, I can take X and Y to be one object. Good. So we're looking at this picture. Then I do a braiding, right, between X, Y, and Z. I did the braiding. What do I end up with? Z, because Z goes here, so Z on the left, then X tensor Y. Very good. Now if I just re-bracket, I get what's here. And bracketing, again, doesn't matter. Now let's do this other path. Okay, I leave X alone, right? I take this to here, to like this level. So I'm just moving up like this. X, nothing happens to it, identity on it. But Y and Z, what happens to them? They get braided, right? They get braided. And it's denoted here. Then alpha tells me, okay, I can look in, instead of looking at these, I look at those. And now Z comes here. So this line is Z. Hope the camera can capture that. Z is here, and this is X. Now I braid these two, which is what's done here. And Y just is left alone, nothing happens to it, and I end up with that. So the diagram commutes. That is the same as that one. Very nice. I'll consider that as a proof. It's good enough to be a proof, so. Very nice for our purposes. Yeah. You can go through each individual, just applying all the rules that we mentioned, and write it out, and you see you'll get this, but that's a bit tedious, so I like the other method. You just stare at it long enough until it makes sense. Nice. Okay, any questions? Proposition. Point 19. Okay. C is a braided monoidal category. Very nice. Now, the Yang-Baxter equations. Yang-Baxter equations. And sorry if everything is so abbreviated. I abbreviated for the talks, but in the notes it's less abbreviated. Are these. Okay. Should I write it? Yeah, I'll write it here because. Yeah. Okay. So start off with X, Y, and Z again, and want to leave room in it. X, Y, and Z, and X, Y, and Z. So, and the camera should be able to capture that. Hopefully. No, that's wrong. I was like, why is it looking like the first one? Is the same as I didn't continue this line yeah, in the notes I didn't continue this line. Sorry about that. That's another typo, but I guess it's kind of implied. It's not a huge typo. Yeah. Now, says these two things are equal. Now, why is that so? What is this telling us pictorially first? Well, if we look at, or if anyone wants to go. Okay. Yeah. So just imagine this in terms of like knot theory. I have these strings, and the over and under crossings are like this. So if you look at it long enough, you can see that what's happening here is this y going over z. I'm just sliding it back here. So first, y goes over z, and, well, nothing happens to them. But then x goes over both of them. Whereas here, x is going over both of them, and then y goes over z. And you can actually prove this kind of nicely if you just get like 3 strands of strings and like glue them to the table here and like there, and or like maybe elastic bands is easier or whatever, and just try to slide this here. So you make this over and under crossing happen here instead of there. It's kind of like if I take this and put it over there. And this is allowed because I'm not taking any under crossings and making it an over crossing or vice versa. So now the proof for it. So that was a nice way to visualize why you can have that. Now let's actually prove it. Where's the eraser? So this is the cute proof that I mentioned before. That you might feel cheated out of a proof, but it's actually rigorous because we've rigorously defined what these pictorial diagrams mean. So if you want, you can always translate them to their like commuting diagrams and see from there. But okay, proof. So let's start with the left-hand side. That one. Okay. I'm gonna take these and bracket them together. So what's going on? What will happen? Again, we don't write the alpha prime, whatever. So I'm bracketing these two together, so it becomes y tensor z. Right? Nothing happens so far. Then it goes under x, and it goes under x. Then a braiding happens here at this point. So braiding, right? The indices are implicitly implied as y comma z, so I'm not going to bother to write it down. And this is going to be z tensor y, right? And this is going to stay as x. Okay. Oh, did I? Oh, I think. I think. I skipped something. Right. My bad. I'll write it here. How did I not write it down? Neutrality. Yeah. Yeah. Somehow I missed that in the notes. So I'll write it here. Something that we're going to use. It's called naturality. So I guess first remark, a quick remark. So quick detour from our proof. But symmetric, when Jaden mentioned if you braid twice, We talked about being symmetric. Symmetric. If you braid twice, right, this is I braided twice. If it's symmetric, it means that it's the same as this. You can take this undercrossing, make it an overcrossing, and just move the string to hit this side, and you get that. So this is what it means to be symmetric, pictorially. Nice. And naturality. Naturality is what is if I start with x and y and have a g here, gives me x prime, and this goes under, an f here that gives me y prime. My board work isn't the best, sorry. It's the same as if I just slide these harms down the strings. So I have x, I bring g here, and then do the braiding, right? Here I have f, started out with y, take it, and the braiding is done later. So this is an x, yeah, x prime, right. So it just tells you can slide this down on the rope. That's what naturality tells you as a condition. So yeah, it doesn't matter if I do it, act on the objects with the harms first, then braid them, or I braid them first, then do that. It's the same thing, right? Because I'm not making this undercrossing to an overcrossing, so I'm not doing anything illegal here. Now, right here we use naturality. To get what? To move this braiding down here. Okay, so I get y tensor z, and this is x, and goes like that. There's a braiding, again, the indices are implied, yz, and then the under and over crossing happens. And so this will give me z tensor y, and this is x, and that is equal to, just write it here, equal to, I just like expand it in terms of, well, I have y tensor z, so I just draw the two lines down. I get, there's a braiding that happens here, right? This is my y, this is my z. Instead of treating it as one thing in the bracketing, again, bracketing doesn't matter, write down both things. Goes up like, I really don't leave myself enough room for these things. Like that. And let me try to distinguish those. So yeah, this I expanded as y and z. The braiding happens here, and then both of these go under x, which happens here, go under x, and this is the right-hand side. End of proof. QED. So it's really nice because it's like half a line. I wrote really big, so it seems more, but like it's just like 3 under and over crossings, and you're done. End of proof. Very nice. Any questions about the proof? Okay. So those are that's the Yang-Baxter equation. Very important. and I've been told by the physicists that it gives you solutions to equations of motion or something, or the solutions are equations of motion or a family of them or something like that. But I don't know. Yeah. If anyone knows more about this, please intervene because yeah.
Like a motivating physics sort of example from all of this. So categories representations for an algebra will be, that's a category, right? If you have a bi-algebra structure, so like a coproduct or co-unit, that actually induces a monoidal structure, right? Because you can apply coproduct, apply a tensor, right? And actually, the braided structure, if you have category representations of some algebra, a braiding is exactly the structure of a quasi-triangular, is exactly an arc matrix. You can actually induce, you can infer an arc matrix on your algebra, and the braiding relations are exactly the equations the arc matrix has to satisfy, so it exactly becomes the Yang-Baxter equation. So solutions to the Yang-Baxter equation for representations exactly become different braidings on the category representation. So these braidings that you see here are very literally all particles. All very particle stuff.
That's awesome.
Yeah.
Nice. So okay, there's physics here as well. Nice.
Yeah, like these are like diagrams of particles moving off the board.
Yeah, that makes sense. That makes sense. Going up the board, yeah, that makes a lot of sense. Personally, I'm more motivated by the math, but it's good to know that there's things here that are fruitful for the physicists. Well, the word promises in quotation marks. So, yeah, it's kind of tongue in cheek. Okay, I think actually we're doing good with time. Nice. So, okay. Definition. So, C and C prime are monoidal monoidal categories. Are monoidal categories. Now, a monoidal functor, a monoidal functor from the first category to the second one consists of a functor from f that I wrote there. It's fine. From C to C prime. A natural transformation. A natural isomorphism from the product of these two categories. So I'm going to use act on each one of them with the functor to get C prime cross C prime. And the monoidal product gives me one copy of C here. And if I act on it with the functor again, I get C prime. And here I use this is the monoidal product in the this other monoidal category C prime. And so there's a natural transformation, so a natural isomorphism, mu, that goes from here to here, such that the diagram, okay, we have a lot of commuting diagrams. Okay, and also epsilon. For a second there, I thought we were done, but no, it can't be that easy. So epsilon just takes the unit here uh, to here, and it's an isomorphism. Okay, such that these nice diagrams come in. So this is prime because we're doing this in the prime category, because remember the functor sends this from the unprimed category to the primed category. That's why there's the prime here. So this is these operations are done on the level of the prime category. Prime, that's why we see all these primes here. Tensor prime F. Again, you can re-bracket, which is nice. Tensor prime Z. Now I can use the mu I have on, well, on this I do ident. Oh, there's another typo. I forgot to put the identity here. It's fine because it's kind of implied, but I think it would be nice to have that. Actually, give me a second. Sorry. Yeah, there should be an identity here. I didn't write it here because I think it's just in place, so I'll just stick with that. You leave this alone. X it's happening in the primed category, so that's why, again, primed. And this brings in the y and z into one thing. Now I can do mu again. On x and y tensor z, so it's one object. So I can put both of them in the same functor here, x tensor y tensor z. And what can I do here? I act on it with mu xy. So it takes in those things and gives me one functor acting on x tensor y. And that I just leave alone. And so I do mu again. Here, mu acting on x tensor y as one object and also z as the other object. So I just bring all of them into one functor. It's going to be x tensor y and z. And so now I can act on this with is that right? Yes, but the functor acted on the associator. Yeah, should be correct. Okay. I didn't need to write down the indices, but I did. So the associator. Right. I don't think I ever said the name of the associator. Maybe I did. But either way, thank you for bad with names. But yeah, alpha. The rebracketing is called the associator. I can rebracket this, goes from here to here, and yeah. So this diagram commutes. And so I start off with that, and yeah, using mu, I can throw them into inside of the functor, and the associator helps me to rebracket stuff to make things work out. So I have that, and there's one more diagram. That, and if I have one, again, it's happening on the level of the category of the primed category. That's why we have the primes here, just to not throw people off. Why the primes? Because again, the functor sends the these unprimed ones to the primed ones here. If I act on it with epsilon, I think it's mathcal E technically, I don't know. And identity on that, this gives me by how I defined it over there, functor applied to 1, and because we're in the codomain, again, primed category, get that. Now, I use my mu to on 1 and x, and it just throws in them into the same functor. So this will be 1 tensor x, and here I take the right uniter in the primed category, in C prime, and this gives me this, which is nice. And the right uniter, but in the unprimed category. So this has to be like that. Right uniter in the unprimed category takes in 1 tensor x and gives me x. And we want these to commute. Okay, and you have the same diagram for L, analogous diagram that we just won't bother to write down. The point is, you can go from here to here using just the right uniter on the unprimed category level, or going through all these shenanigans here to go there. And you have the analogous diagram for the left uniter, but no point in writing that down. Okay. Right, and okay, so this is the last thing, and we're almost out of time. We are out of time, so this is the very last thing. Yeah, I also don't want to, that's not, that was my fault, not people's, so that's why. Okay, right, so we have that. That's the end of definition. I should put the thing, end of definition, right? Okay. So, if C and C prime are braided or symmetric monoidal categories, F, end of sentence, F, the functor is called braided or symmetric, respectively. Right. So if it's braided, symmetric, if and only if you have this commuting diagram. So you act on it with the braiding in the primed category, swaps these, right? Y X, okay? And you use mu that we have there on Y and X to throw these into one thing. Y tensor X. And, right, mu here as well. Mu on XY this time. What do you get? It throws it into the functor, like so. And now you do the braiding, but on the unprimed category. So this is going to be F applied to the braiding. So it takes in these two, braids them, and yeah. And the for the picture of this, write it here. Draw this line here. We start off with what? It's not the picture of that, is it? No. That's fine. It's the picture of that. Okay. So we start with the functors of x, y, and z, the functor applied to x, y, and z. And z. Y and z. So what happens here, my mu takes in these two. Right, mu, again, it's implied that this indices are x comma y, takes in these two, spits out what? Throws it into one functor, so f of x tensor y, right? And then this just nothing happens to it. But then there's another mu. Again, it's implied that the indices will be x tensor y comma z, right? And this will give me out x tensor y tensor z. And then there's an f alpha here because here to get that. And on this side, what happens is these two, you act on it with mu, you get the functor y tensor z, right? And this nothing happens to it until here, where mu again, it gives you f x, then these two, right? Sorry, tensor, y tensor z. I didn't write the last step for over here. The alpha just swaps the bracketing, so you get f x tensor y tensor z. Sorry, z. And this is that, right? It looks nicer to look at this than to look at that, in my opinion, at least. But you can see what I just did there is I drew this in the new nice way of denoting things. I
You said
acted.
before that alphas were implicit in
Yes.
TQFT didn't write those diagrams.
Yeah.
Could you say even f of alpha could be omitted?
Yeah.
Is that unambiguous?
Yeah. I guess. No. Yes, thank you. Good question. Because, yeah, the alpha. Okay. Alpha prime would be emitted, right? So these are objects in the primed category, right? So if I'm doing rebracketing on this level, that would be emitted, right? We don't have to worry about the alphas if I was rebracketing here. So this, I would use an alpha prime, right? Not an alpha, right? Because this is happening, each one of these are objects in the primed category. So I need an alpha prime to take this bracket to here, right? Yeah. So for those, yeah, alpha prime and alpha prime inverse are emitted because we can rebracket however we want. But alpha here, in this new context, in this thing that we're working on, is not done. Is done on the level of the unprimed category. So here, alpha still matters. That's why we have it here. Maybe you can omit it later down the line in the explanations that I saw. Maybe later on we just say, okay, we're mature enough to not worry about that and drop it. But I saw kind of like a warning about this because if it was an alpha prime, so if it was done on this level, yeah, you could. So this doesn't matter, right? What is this in this picture? What's going on there? What's going on is that instead of bracketing these two together, right, you start off with these two, then this. Instead of doing this, you do this. So here we use the alpha prime, right, on the right-hand side, but we didn't write it down. It doesn't matter. But bracketing inside of this functor before we apply the functor to go to C prime, so when it's done on C, is still, I guess, important, I would say. That's why we left it in there. Yeah. I guess if we didn't write this and we get that, we could figure out that, sure, there has to be an f of alpha because we need to rebracket to get this thing. So we could probably reconstruct it, even though even if I were to erase this, but yeah, that's a good question. I haven't thought much about it, but yeah, that was a comment in the course that was given. Yeah. So just to be safe, I would say no. We can't ignore alpha. We can ignore alpha primes as we did here. We can't ignore alpha, but maybe we can.
Yeah, this is a diagram in C prime, right?
It's a diagram in C prime, yes.
Yeah, so the diagrammatic sort of language only allows us to omit the coherence isomorphisms in C prime, right? But we don't know that f of alpha is a coherence isomorphism in C prime, right? It's not one of these alpha cells in ours, so the calculus doesn't let us formally omit it. Intuitively, we might not care, but formally,
Right.
it doesn't let us omit it. So yeah, we go draw it.
Yeah. Yeah. But I guess, yeah. If I were to erase this, we could probably figure out there has to be an f of alpha there. So, but yeah, I guess formally in the rules we can't omit it. So, yeah. Yeah, I think that's it. A bit over time. I apologize for that, but I got to everything that I mentioned in the abstract, so that's nice. Yeah. Any questions? Nice. I hope you're enjoying this. So, the Dalhousie, like Theo's TQFT 2026 summer school is coming up, and I'm going to that. So I was thinking of progressing in this series of TQFTs as much as possible. That's why next week I'm also giving the continuation of this. I thought if people want to progress as much as possible for TQFT before the summer school, but I don't think anyone here is attending besides me. I thought if people wanted to, I could give more talks during the week. If people want to. Does anyone want me to give more talks? I'm already scheduled for next week, Monday, and the summer school happens the week after that. So not next week, but the week after. And yeah, does anyone want to for me to give more talks?
I mean, I think this topic is interesting. So whenever you're free. Yeah. There's no like
Okay.
pressure, but
Yeah. I mean, it would be beneficial for me to give talks on these as well, to prepare myself for the summer school, and if people want to, yeah, for sure. So, do you guys have a preference for the time? Because the regular ones are just Mondays, 4 p.m. But if we're doing in week, I wanted to not, obviously, I would put it such that it doesn't overlap with the Math Phys or QFNS seminars. But yeah, if you have a preference.
I'll let you know my constraints on when I have to go right now.
Okay, yeah, thank you for coming. Yeah, nice. Thank you for coming. Thank you.
So we can stop recording.
Yeah, go for it.
The button?
Yeah, the stop
Okay.
record.